Page 19, yes, thank you. Because we're having trouble cutting this set up without being distracted, I'm going to ask for voices off and until we get all kind of like settled so that we can save some time. So I need out your notes to page 19. Today we're not doing a do first, that's like a review of yesterday's class because we're going to try to jump straight in. So this is where we're going to pick up the lesson, but I want you to take a look at it silently on your own and see if you can figure out any of these like symmetries, and we'll talk about it in a second. While I'm doing that, I'm going to pass out your problem set that is graded, and we will talk about in a second a few things that I noticed there, okay? So voices off, taking a look at your notes or getting out all of your supplies. We'll also need calculator, so again, get out your calculator again if you don't have it already out. Michelle, help me out because I don't know all the... That's from Michelle. Hush, hush, hush. Kaylin with an Because we're distracted. We're talking about other things. So we're going to transfer. Where did Jennifer go? She, OC, Carlos, Jeremiah, Angela, oh man, they're all over there. Keep going. Samantha, Perez, keep going. So you're silently looking at your problem set. You're silently looking at this stuff about symmetry to see if there's anything you can figure out before I start talking. I might answer your question in a second. I'll see if you have. Yeah, we got one other one. The bottom? It was just the quadratic formula. You can't do the box. You gotta do negative plus or minus. 1 second, I passed mine up on my agenda. What's that here last time? Yeah. Alright, we are going to take a look at a few things. Alright, on your problem set, there are on the front 2 numbers, plus blah, that you would have gotten if you check out your rubric in your syllabus. Every problem set is worth 15 total points maximum. First number is maximum 5 points for completion. Okay? I, for the purpose of this problem set, did not look at that back page because of what we talked about with the back one, like we kind of like rushed through on Friday. So I only looked at the first like 3 pages for your completion. If all of those were attempted, you got 5, and then following the rubric, I like started taking off points if there were problems you skipped, okay? On the second number, plus blah, that should match if you go through your packet and add up your little pluses around. That should add up to that number, and that's how many points you got for accuracy, and that was a total of 10 possible points, okay? And then those 2 numbers, let's say you got like plus 5, that means you got a total of 10 points. If you look at the rubric, it says like 10 points is an 8.25, I think. Or you got 15 total points, so you got a 10. And you can look and you can make sure I didn't like randomly write the wrong grade with your points or something like that if you're curious, okay? So check out the rubric, that's how I graded it. And then sometimes it's confusing of how many it was out of, so I tried to write like plus 1 out of 1 or plus 1 out of 3, depending on if a problem I checked multiple things, okay? On the front page, biggest thing I noticed, like across the board, more than just a few people missed, on the one towards the bottom, was a lot of you said, it's a maximum, woo! But then if you read the directions carefully, it said, find the value of the maximum, which means I actually want the point, the vertex, and so I needed you to use negative b over 2a. A lot of people just looked and they were like, it's around negative 4. But you have the equation, and if you plug in negative b over 2a, it's actually not negative 4. It was really close. It was like negative 3.875 or something. So I just wanted you to like pay a little bit more specific attention to that, but we should have that all cleared up. And then other than that, I did not grade of the ones that you had to solve. I didn't grade number 7. But I know there were some people that like attempted that one, but then I could tell they got stuck. On that one, the box method, that's one of the ones where the box didn't work, and so you had to then go use the quadratic formula, negative b plus or minus square root of b squared minus that whole thing. Okay? So in general, take a look at everything, and if you have questions about one of the problems specifically, or your grade specifically, I'm going to take Omar's only, and then I'll divert you to meeting with me after.
Do you remember what the answer to number 7 was?
The one that was the square rooty one?
Yeah.
It was something with like root 15. It wasn't a root that you would know. So I have either, if you want to see my key later, I have the decimal.
2 square root over 15. 2 square root over 15?
I don't know. Sorry. I can try to make something up, but I actually don't remember. So let me look at my key and I'll just get back to you. I could even know more if we're practicing later and I have a second, I'll look it up and then I'll tell you. Okay? Okay, so you guys hold on to those. And problem set 2 is on its way. You're working on it throughout the week. On its way to me on Monday. Oh, all right, symmetry, woo! Today we're going to talk about symmetry. So before we jump in, another good thing you might want to have out, I'm going to be giving lots of participation stamps, so I see a couple people like, Elena got them out. So let's start off with, in general, who can just tell me what symmetry or that word means to you just in the English language? What does it mean if someone says something symmetric or has symmetry? Just in your best summary in your own words. Jason?
It's equal, like if you were to fold it, it would
Cool, I like the fold idea. So something about folding, it being perfect or equal. Anyone else want to build on that? Another opportunity? Nobody. All right. Oh, Natalie, yep.
I was going to say, if you flip it backwards with a wire, I would be exactly the same.
Okay, so something about like the points being the same across a certain X or Y or something like that. Okay, interesting. When you were little, maybe you did kind of like along the lines of the folding like you're saying. You might have like folded a piece of paper and along the fold like then cut like this part of a heart, and when you opened it up it was like nice because it was symmetric because your heart was the same on both sides. Anyone do that? Oh, back in the good old days. So that would be something that's like symmetric, the shape on either side, right? So we're looking for things right here that's symmetric with respect to or across certain lines or points. In this example, my dotted line almost looks like it's like vertical. If we were to like put this on a graph, does that look more like the x-axis or the y-axis?
The Y.
The y. So this would be an example of if I opened it up, something that's not perfect, right? Because I didn't actually cut it. I drew it and it was not symmetric. That looks a little more than the other one. But in general, let's take a look at these graphs and see if we can come up with something that looks like perfect y-axis symmetry. Anyone got any suggestions? Christian? Where'd my stamp go? B, he says, is correct. Anyone see it?
Yes, it's over there.
Where?
Over there by the computer.
Oh yeah, good eye. I didn't even remember walking over there. Okay, correct. B is kind of like my heart. You can see that it's reflected over the Y. Anyone see any others? That it could have multiple. So anyone see another one that would work if we folded along the Y-axis, Rhiannon?
A would work.
A would work as well. If you kind of picture like Jason said and you fold it on the Y-axis, it would match up the circles on either side, right? Okay. Time for the next one. X-axis. Anyone see OC? C.
Anyone see C?
Cool. And you got another one, Cindy? Also, A again. A is pretty special because I could fold it that way as well, and it would still look the same on the top and the bottom. Okay, last one, origin. This is kind of maybe the weirder one, Pedro.
D.
Process of elimination and maybe looking at it. D. All right, let's talk a little bit more about that one. Anyone think maybe another one works for D as well? Alicia?
I was thinking A.
A works for that one too. Cool. So let's talk about why it has origin. Where is the origin? 0.0. So it's like this point right here. This means that that's not a line to reflect across, but it's a point. So what they say it's more like rotating 180 degrees around that point. So like, you know, like 360 is like a full circle and a 180 is like a half circle. So you just went a half circle around the full graph. Okay? So we got x-axis, y-axis, and origin symmetry that we're going to be talking about today. And I have my handy poster that we're going to be referring to. Maybe I should put it up higher.
No.
No? But it's so pretty. Let's see if I can figure this out.
There's the little clip on the top of
Uh-huh. Sorry, y'all. Scared the whole thing on. Okay, cool. So we're gonna also learn some of this other stuff, odd, even, all sorts of interesting things. Very exciting. Moving on. On your problem set, there will be 2 problems tonight from this lesson, like the next 2 if you're going in order, and it's kind of sectioned off so you should be able to see, and I'll show you at the end of class really quickly that. Alright, moving on. Let's get down, this is going to be in the way, let's get down some more definitions kind of with x, y, and origin, the stuff we just talked about, okay? So right here, if you've got graphs of relations, they can have 2 different types of symmetry. Graphs with line symmetry can be folded, like you said, along a line so that the 2 halves match exactly. So example of that we just had was either y-axis, that's a line, right, that we could fold along, or the x-axis was 2 types of symmetry we just talked about, okay? Graphs that have point symmetry can be rotated 100 degrees with respect to that point and appear unchanged. So what was the example point symmetry we did? Origin symmetry, because the origin is a point, it's not a line. Okay? So that's kind of like the 2 groups, and we're talking about 3 different types. So here they are again, the x-axis, the y-axis, and origin. And kind of like someone said, I think Natalie, if we take a little look closer at x-axis symmetry, it happens if and only if for a point x, y, you have kind of that reflected point down here, so you have x negative y. Like for the same x, you have the positive y and you have the negative y down here. That means it has x-axis symmetry. So algebraically, you can know that by looking visually, but let's say I didn't give you a picture, I just gave you an equation. Algebraically, we're going to learn today that we could replace y with negative y in our equation, and it shouldn't change the equation. We should have the same relationship. So I'll show you an example of that, because you might be like, I don't know what you mean by replace y with negative y. So if we have this graph, this would also have x-axis symmetry, right? An example of an equation of a parabola that's sideways is x equals y squared. If I take this equation and I don't know what the picture looks like, I'm telling you it looks something like that and it works. But if I algebraically replace y with negative y, what do you notice happens when we square that negative? Becomes positive, and so when I simplify this, I actually end up with the same thing I started with. So that's what I mean by when I replace y with negative y, I get the same equation. Okay? That's going to happen whenever we have a x-axis symmetry. Cool? Okay. Y-axis, similar but different. if you have a point xy, if and only if xy on the graph, the point negative xy is also on our graph. So this time, for one y, we have two x's, x and negative x reflected. Okay? So we could replace instead x with negative x, and we should get the same equation. Pedro, I bet you can come up with an example of that. What would be your example equation? Yeah.
Y equals x squared.
This time y equals x squared. Oh, because that would look like this. But if we didn't know what it looks like, we could replace x with negative x, and we would get back the same equation. Right? Cool. In this case, if I replace y with negative y, that's not the same equation, right? And so this does not have the other symmetry, x-axis symmetry. It has y-axis symmetry. Cool? Okay, last one. Origin symmetry. That's when we have xy and we have negative x, negative y, because we rotated a full 180. So if it was in quadrant 1, it'd be in quadrant 3. And so we're going to replace x with negative x and y with negative y. And negatives should cancel or do something fancy to where we get the same equation. Okay? Let's talk about one example of that to wrap up this part of our notes. An example of something that would have origin symmetry. Actually, anyone know what, like, parent functions? We're going to talk about those later in the unit. But anyone, this looks kind of like one parent function you might have seen, not x squared. Anyone know, Laisha?
You're asking what a parent function is?
Okay, yeah, let's start there. What's a parent function?
I think it's whenever it's similar, but it's slightly different.
And then we like can move them around and do stuff. So there's some key ones you probably looked at, like absolute value of x, x squared. You've probably looked at, other than blanking out, maybe you've looked at 1 over x. You've looked at some, and this might look similar to one. Anyone happen to remember if it's like this curvy thing right here, what the graph could be? Cubed, x cubed, looks like that. A cubic. So y equals x cubed is an example of origin symmetry. And let's see by plugging in some negatives. If I plug in negative y and negative x for this one, negative cubed, negative times a negative times a negative is going to be a negative. So it's just going to stay negative. I'm going to draw my parentheses now because it's to show like I already cubed it. Okay. And now I could divide by like negative 1 on both sides, right? As long as I do it to both sides, I'm good. And I'm back to the same equation, right? Like the negative on either side can cancel each other. Cool? So I actually have to replace both if it has origin symmetry for it to work. Okay? Alright, so that's the 3 types of symmetry. So what we're going to look at right now is some examples, and you guys are going to be helping me identify which type of symmetry, but then we're going to focus a little bit more on proving algebraically that that's the case, because this might be the part that we're still going to like about. Okay? Alright, so here's the first example. Example 1. Geo. Do I always pick you to read? Sorry. I don't know, I feel like I keep calling on you, but can you read for us where it says use the graph, nice and loud?
Use the graph of each equation to calculate symmetry with respect to the axis, y axis, and the origin. So put your answer numerically and then confirm algebraically.
Okay, so for the purpose of today, kind of save some time, I'm actually not going to have us like examine numerically. I want us to focus on looking at the picture, figuring out like visually what we think, and then confirming algebraically, either replacing negative x, negative y, or both, to see if our equation ends up the same and if we're good to go. Okay? So, looking at this graph, really quick, take 20 seconds and turn and with your neighbor really quickly, figure out which one you think it is, and then write down which one you think it is, x, y, or origin, and then I'm going to pick someone from the popsicle sticks to share. Okay? Turn talk with your neighbor, 20 seconds really quick. Talk to your neighbor. Which one is it? How do you know? I'm going to pick someone, 10 seconds. Is this our class? Yep. Okay. Okay. Kaden with an A. Over to you. Which type do you think? X, Y, or origin? X-axis. People that agree? People that disagree? What do we think? I would agree as well. Symmetric with respect to the X-axis because it looks like it's reflected from top to bottom if we fold it along the X, right? Cool? Okay, now we get to the confirm algebraically. We said earlier that if we reflect across the X, that means algebraically we can replace, if you go back in your notes, Y with negative Y, and we should get the same equation. So let's try to prove that and see what happens here. If I replace this Y with negative Y, let's write that down, X minus negative Y squared. When we simplify it, is it back to the original equation? Let's check. Negative squared becomes positive, so we'll have X minus positive Y squared equals 1. Is that the same thing we started with? Yeah. So it has X-axis. If we would have replaced this with a negative, it wouldn't have gone away and we would have had something different, right? But this one stayed the same. Cool? Happy? Okay. Using that example, really quick, look at this next one. And with your neighbor, I want you to, again, you can skip this part, but I want you to figure out by looking at the graph and then see if you can prove it algebraically. Okay? Go for it. Yes. You just observing? I mean, that's fine as long as you're producing it. So far, I haven't really seen problems that we're doing. So, I mean, I don't even go if you go or not. There it is! You ready to give me? Oh. Right, okay. So, as long as you can, you have to do these practice questions. If you want to fill in the blanks, that's your video. But I'm going to be able to make sure you can solve the problem. Cool? Okay, question? Because the rule for x-axis is that if I replace y, there it is. This is what this is. Yeah. If I replace y with negative y, I should get the same thing. Okay. So and then for this, for y-axis, we replace x with negative x. Origin, you want to replace it. Cool? Oh no. Yes, yes, yes. You're good. Across what? What do you mean by this? Like straight down?
Yeah.
If you did that, would they be on top of each other? This would be down here, so it wouldn't. So we almost want to fold across the origin. You're right. Good job. Good? So that means for origin, put back to origin. You want to replace origin x negative x and y.
And it's some good stuff that happens.
So that means that we have a negative here and a negative here.
I started in
No, there's no squared in this equation. If the equation has squared, then you're going to square it. You're going to just plug it in places, right? And then notice the negative and a negative. Oh, cancel the positive. X, y. Perfect. And what happens when you have a negative and a
What else
negative?
do we do? You watch the news?
Nope. Just the x and the y. It doesn't say replace the negative with the negative. Which one? Yeah, check each other. Okay, write that down. Cool. And that's not a subtraction sign, right? That's just like multiplying a negative x and a negative y. So if I'm multiplying, so you should just plug it into both. Because if you put back for origin, it says replace x and y. Okay? So now we've got a negative times a negative is a positive. So we just got positive x equals 4. It's the same thing. Levy? Take care of your business. Put it away. Sorry. Do you all are all fine. Just talk to Levy. Loudly.
We're nosy.
Put it away. Or I'm going to eat your book. Okay. This is good. So this is for looking, right? So now origin, algebraically, what that means, because of this relationship right here, is that you put in place in front of x, and then on y, you'll get back the same equation, but we did x. So if you come here,
And then right,
instead of this algebraic form, so y, you put negative in both of them, then they end up canceling, and you end up with the same thing. And x times negative y. Equals 4. And now actually they're like, so and that's positive. This goes with a negative 1 in front of the x, and a negative 1 in front of y, right? So we can multiply this, and negative 1 times negative 1 is positive 1. Right? And this same thing in place. That means nothing changed. Negatives cancel each other. If you plugged it into one of them, they wouldn't have canceled, right? So if you plug it into this one, saying that it's y-axis symmetry, you're not going to get the negative. So we're just symmetry. Okay, cool. All right. Let's take a look. See what we came up with. Break my heart. Do your work, people. Don't break my heart. Please. Makes me so sad when you don't practice, because then I know what happens. You take your quiz, you raise your hand, and then you ask me the question, and I can't help you. Okay? Please practice. All right. XY equals 4. Christian, what do you think? Nice and loud. One more time. Origin symmetry. From looking, it's symmetric with respect to the origin, but then we're like, I'm not sure how to prove it, so that's what we're practicing as well. In order to have origin symmetry, what do we have to do to prove it, Laisha?
You have to turn both x and y negative.
Cool.
So you put parentheses negative x, and then parentheses, and then parentheses negative y, parentheses and 4.
Cool, so we don't change the number, right? It doesn't say make all the numbers negative. It says make it a negative x, make it a negative y. And if it has origin symmetry, using some algebra, we should get back to what we started with. And if we take a look and we have something negative and something negative, we end up with positive xy equals 4, which is what we started with. Okay? So that's like a proof of the fact that it's origin symmetry. Okay? All right, moving on. Let's talk about, now we're going to enter the realm of functions. All the things we've looked at so far have just been equations. They have not necessarily been what we can call functions. Remember the other day, we talked about this word function and said that certain things we're going to look at are functions. Okay? These are functions. Graphs of functions have either y-axis or origin symmetry. Uh-oh, who did we leave out? X-axis. So, in this box right here, it asks you a great question. Thanks for asking, notes. Why can't a function, I'm gonna wait just so I can make sure everyone hears the question. Why can't a function have x-axis symmetry? So here's something with x-axis symmetry, right? Based off of, if you can remember back to what we said, I said a function was. Can anyone here remember why this graph is not a function? Why something with x-axis symmetry is not a function? What do you think?
It wouldn't cause the vertical length.
it wouldn't pass, come give you a stamp, the vertical line test. Remember we said that an x value can only have one y value if it's a function, right? And see how this has two y values for every x. And so automatically, if it has x-axis symmetry, it's going to fail the vertical line test, and it will not be a function, okay? So now that we're in function land, this is not a function. We're not going to talk about x-axis symmetry anymore. We're going to focus for the rest of class on origin and y-axis and learn two new terms, odd and even functions, and talk about what it means for a function to be odd or a function to be even, okay? All right, function land. Here we go. Functions that are symmetric with respect to the y-axis are called, this is actually already filled out on your notes, sorry, I forgot to make a blank for you. They are called even functions. Okay? So if you identify, ooh, it's got y-axis symmetry, it's actually what we can call also an even function. Kind of like synonyms, they go back and forth, okay? Functions that are symmetric with respect to the origin are what we call odd functions. And so if you're trying to sort out which one's which, origin odd, oh, origin odd, and then even is y. Cool? Origin odd, even y. Okay? So what does that mean? You will have to identify a lot in pre-cal whether a function is even or odd, which means you're kind of just looking at whether it's symmetric with the y or the origin. Okay? And then you will have to algebraically prove one of these two things, which is kind of what we already did when we started plugging in negative x's and stuff. Okay? So we're going to talk a little bit more about the algebra behind this. Let's talk about even functions. Now I'm going to use function notation, okay, and say that when I plug in a negative x to my function, f of negative x, I should get regular f of x. It should stay the same as the original f of x. Okay? So let's write that down. I can plug in, so that you know what this means, negative x. Running out of room. And simplify to get original function. So you should get back to the original, like if it was x squared, you should plug in the negative and you should be able to get back to x squared, right? Okay. For odd functions, we're going to change things up a little bit. Earlier we said for odd functions or for origin symmetry, we plug in both negative x and negative y. Okay. Another way to say that, which is how they typically, like by convention, prove whether something is odd, is if you plug in just a negative x, that means your y is going to be negative, right? We said negative x and negative y, which means you're going to get the opposite of like the original function. You're going to have a negative f of x. We'll see an example in just a second. Okay? So if we plug in negative x and simplify, we will get like the opposite, or the negative version, like a negative y is going to pop out. We're going to get an opposite of original function. Should have said opposite of. There's like a word missing there. Okay? So if it's x cubed and you plug in a negative, you know how that negative comes out front, right? And so you end up with like the negative, the opposite of what you had before, x cubed. Okay? Let's look at a couple of these proofs and see how we feel. Alright? First one. Up first. X cubed minus 2x. Stick with me. This is where these examples are going to be very similar to what you'll see on your problem set. You'll see two of these on your problem set that you can knock out tonight. Okay? What it asks you to do is actually like 4 things in here. So let's make sure we don't miss any of them. It says, Using your calculator, ooh, we need to use our calculator, that's why we brought it every day. Using your calculator, we need to graph the function. I didn't give you the graph, so the first thing you're going to have to do is graph it, okay? Next, analyze the graph to determine whether it's even, odd, or actually it could be neither. Is everything in the world symmetric and perfect on both sides? No. So it'd be nice and pretty, but it's not. So sometimes it's going to be neither. We haven't seen that yet, but it will be. Third, it asks us to, so it's not good enough just to look. It asks you to actually prove it algebraically, which is where we're going to, again, focus our time to make sure we understand that. And then last, it wants you to, therefore, once we know it's even or odd, we know whether it's origin or y-axis. So we want to then identify the symmetry as well, which we kind of already did with the first step, because they go together. Okay? So let's take a look at this one. If you haven't already, go ahead and graph this in your calculator, and while you're doing that, I'm going to quickly check, make sure we got them, and see who didn't have it yesterday, and who has it today. Gio, thank you for getting yours today. Do you have yours? Oh, it is a student homework still? Okay. I need it tomorrow. Charles ready to go.
I'm a
Okay.
good friend, so.
You are a good friend, but no participation for that. Good, good, good. Do you have your calculator? Okay, buy-in. I'm writing that down. I'm going to check in with you. Still waiting? Okay. Good. Good. You got it graphed? Still loading up? Got him. What's down there? Got it. Good. Huh? Okay. Can we get those for, like, by the end of the week? Good.
Is that home advice for good?
What would you be honest
What do you think?
Wait, is that being honest? Wow, you're so honest, bro.
Just take out your calculator and say, yeah, I got it.
Unhonest, dishonest, some shit. You want to borrow my batteries? I have batteries.
Alright, here we go. Oh, here it is. Yeah, you got it. Okay. Back to the front. Voice is off. 5, 4, 3, 2, and 1. Alright, up here at the front. Your graph should have looked something like this when you graphed it. If you needed to adjust your window, I can come help you with that. But looking at the picture, even or odd, first we can like make a claim of what we think, but then we have to prove it. So Javier, what do you think, even or odd? Odd is origin, even is y-axis. Odd, because it has origin symmetry. So if you want to go ahead and write down both, I think you can kind of knock out number 1 and number 4 and number 2 all in one go, right? We graphed it. We said it's odd. We said it has symmetry with respect to the origin. So we're missing one piece of our instructions, which I will be looking for whenever I'm grading. I need to also, by describe, I mean, right here I described the symmetry. So try again. What did we miss? Confirm algebraically. What that's asking is to tell me either f of negative x is negative f of x, or f of negative x is f of x. You've got to do a little proof here. So we're going to talk about how to do this proof. That's where we're going to hang out for the rest of class and then practice. Okay? Because we said this is odd, right? Yep. We're trying to prove, the goal is to prove that f of negative x equals negative f of x. It's the opposite of the original function when I plug in a negative. Okay? Let's try that out. So I want you to actually write f of negative x equals, because you're telling me that you're plugging in negative x to the function, just like when we took like f of 3m on, I think, like your problem set. Now we're plugging in negative x. You're going to say negative x cubed minus 2 times negative x, right? Okay. And now with a proof, we literally just take it line by line on either side, showing that like my next line, based off of just simplifying or something, is equivalent to the one before, right? So this one I'm going to keep the same, because I'm hoping at the end that I can get this to be equal to this, right? So this one I'm going to keep the same. On this side, I'm going to now simplify and say a negative cubed. Is it going to become positive or stay negative? Stay negative. If it's odd number, negative, 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 it's going to be a positive times a negative, which is a negative. Negative x cubed. Negative 2 times the negative x becomes a plus 2x. Okay. So we are trying to see if we can get back to negative f of x. So we want f of x to show up somewhere. We want x cubed minus 2x, right? And right here I've got x cubed, negative x cubed plus 2x. Remember how we talked about how you can like pull out common factors, right? So that means I can pull out like a negative 1 out of both of those terms. So what I'm going to do in the next one, because I want to get a negative out front, I'm going to pull out like a negative 1 out here, okay? And say this first term now is x cubed, it's back to being positive, right? And if I pull out a negative out of 2x, now it's back to a minus 2x, because a negative times the minus would be the plus 2x. Do we see how I factored out a negative 1?
Mm-hmm.
Okay, so what do I have here? In this black box, x cubed minus 2x, isn't that f of x? So I can say, last line, that f of negative x is equal to negative, or negative 1, and what can we call this thing? What's the name of this guy? At the beginning, what's his name? F of x. Like this is our function f of x, right? So I have negative of our function f of x. Can we see that? So my goal was to get, since I said it was odd, my goal was to prove that f of negative x equals negative f of x. So you plug it in to all the x's, and then the goal is, if you're trying to prove that it's odd, to get that negative out front. If you're trying to prove that it's even, you would have been trying to prove that it just was equal to this exactly, right? With no negative out front. Okay? If that doesn't happen, you can't get a negative out front, and you can't like have them go away and get back to your original function, it's possible, like we talked about, for it to be neither. Like there's going to be cases where algebraically you're like, wait, I got like negatives that are different than this first one, but not exactly the opposite, where I can pull it out front. Okay? And then you say it's neither. Cool? Okay. We have 7 minutes, which is a lot of great time, to look at B, C, and D. Okay? I want your goal to be to try to get B and C done. If you have time to go into D, then that's great. Practice this, especially confirming algebraically, so that if you're like, I don't understand this negative x thing, you can call me over and I can show you, because tonight, 2 problems on your problem set are like this. Cool? Go forth and try it out. Kurt, then I come to you. Perfect. You, in order to do this, I just want you to put parentheses to show me that you're plugging it in underneath the 4, which means you've got a negative times a negative times a negative times a negative. Each time you have like 2 of these, they become positive, right? So the positive, odd would be positive. So this simplifies to just the negative. Why do you do the 4th? Because it's still on the x. We just did the 4th. It's like a negative, so it needs to go on both sides. And we did it on the negative 1 and got a positive 1. Okay. So then g of negative x is equal Cool? Okay, Catherine, question. Back to this example? Okay. Okay. From here to here? Okay. In general, do we understand how this is odd because it has origin symmetry? Yeah? Okay. That's from looking. So let's say it's a test, and I give you this equation, but I don't give you a calculator and I don't give you a picture. You're like, because you don't have a picture to look at with symmetry, okay? That means you need to plug in negative x, and either a negative you can pull out front, or it's all going to cancel, and you're going to get back to this original function, and that is an algebraic way, so like not using a picture, to figure out whether this is even or odd. Okay, so that's the goal. So when we look at this one, do you see how, Christian, I took negative f of x and I plugged it in to both of these spots? Okay. My goal, because I was thinking it was odd, is to match this one, which says I can pull like my negative out front and end up with this function, but the negative version where I have a -1 in front of this. Okay? So I took the negative, and I cubed it, and anytime you have an odd exponent on a negative, it stays odd. So this stayed negative. Since I had two negatives here, it became positive, right? Okay. Now my goal is to get back to my original function, but with a negative in front. Okay? So what I decided is to get my negative out front in front of parentheses of the whole thing. So when you have something like this, do you agree? You can pull a 2 out front. It's like the opposite of distributing, right? 2x plus 8. You can pull it out front. I'm sorry, Javier. So what I did is I just pulled out a -1, because if I multiply it back in, I have a negative x cubed plus 2x. And then this is my original function, right? And so what do I have? I have negative in front of my original function. So it's all weird, I know. But the more examples I see of this, the more weird the
No, I read it. I just don't do that thing.
you gotta plug it into the last one, and so we're gonna plug it into 14. I guess any of the Javier, question?
I don't like messing up the book.
Do you have another minute? That's still not us. Yep. Perfect. So this means, so this is what you're going to prove at the very end, right? But we can't claim it yet because we have a proof. So we plug in a negative x. You actually didn't plug in the negative x. So when you say this, their first line means you literally have to put it where the x is. Just like how we said f2 means I put 2 in wherever x is, right? Now I can say this is equal to, if I simplify, if I have a negative to the fourth power, it's an even power, negative, 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 it's going to be positive. It's negative, negative, negative. So x to the fourth plus 2. So f of negative x is equal to, what is this? It's our function without a negative in front, right? Is there a negative in front of this? No, everything's the set of plug it in, simplify, and either try to prove that there's a negative in front or that it's back to the same. Alright, we got 1 minute, so I want to get you out on time, so I gotta wrap up a few things. I know that there's a lot of y'all, so I'd like to get you out on time. I know there's a lot of y'all, so I didn't get to answer everyone's questions as you started with some of these proofs. So we will continue to practice even and odd proving, but I want you to look at your problem set and try it out using the example we did and kind of see where you're at so you can make sure you've got this moving forward, alright? Just so you know, this next one was even. For those of you that did that one was even. Alright, go ahead and back up and have a wonderful rest of your day.
Got it, Jason?
No, how do you stop it?
Wait, you might still be better.